Okay, don't worry, I'll record from now. I'll have to do another thanks to you.
Yeah.
Okay, I'll do a little preamble for the other people then. Anyway, such is life. I'll do it tomorrow. Okay, we're looking at the normal distribution. So in fact, I'm just going to go back quickly to Peyton and Sharma, I forgot to record, so I'm going to go through the stuff that we've done quickly again. Otherwise, I'll have to do it tomorrow. And you'll probably from it. Okay, so let me quickly go through it. We're talking of random variables, and we're talking of two types. In this particular case, we're looking at continuous random variable, and the distinction between that and a discrete random variable is a discrete random variable can only take on certain values, like 1 or 2 or 3 or blue and green and yellow, or 100, not 100, but so where a continuous random variable is something like weight or length or time, which is continuous. I'm not entirely sure how I can explain it better, but anyway. And then we define the probability. Let me just share the screen. We defined with discrete variables, which we've done last week or last time, we allocate a probability. A good example would be a dice that you throw. You allocate the probability to throw a 1 is 1/6. To throw a 2 is 1/6. That's discrete variables. With continuous variables, for instance, how long is it going to take you to drive to my house? That it will take you exactly 5 minutes, 3.002 seconds. The probability of that is 0. So with a continuous variable, the probability is 0 of a particular one. But on the other hand, you can calculate the probability of something happening between, say, 5 minutes and 10 minutes. I can calculate that. But the probability of you getting here at exactly 9 minutes, 3 seconds is 0. So there you can see how we defined it. The function, no, where did we do it? Okay, there is where we said it's 0. Okay. So the probability density function, we talk of a density function, any function where the whole area adds up to 1 is defined, can be a probability density function. The total area under the curve between A and B is 1. Okay. Here's another function, the probability that x fall between two values, A and B, again, is this this surface area between, and because if I know the function, this fx, I can actually calculate that. It's relatively simple with maths. Now, the first one of the continuous distribution functions that we're going to look at is a uniform distribution. And a uniform distribution is defined like this. So it's got the same probability from A to B. And to make this work so that this area underneath between the A and the B equals 1, this height will be 1/B minus A. And you can see here, calculate the area, it's width times the height. That's how you calculate this area. B minus A times 1 minus over B minus A will be equal to 1. And that's what we defined. We said this area underneath here must be 1. I hope you can see it. But anyway, that is basically a uniform distribution. And sort of all you really need to know about it. Take note of it. It's not something we're going to focus on going forward. But it's sort of a good thing to understand. You do see my screen, aren't you? Don't you? Okay.
Yeah.
The next one we want to look at is a normal distribution. Now, normal distribution is something that occurs often in nature, and it's a nice distribution, and you can work nicely with it mathematically. And it says that it's the most important continuous distribution that we will consider. Many random variables can be modeled with a normal distribution, and many distributions can be approximated by a normal distribution. So normal distribution is, as they call it, the cornerstone for statistical inference. Now, there's certain symbols that you use when you work with a normal distribution. And we say the mean is, I think, the Greek character for M. So whenever you see a mean, you know you're talking about a normal distribution. And we define, you remember what we said, often a distribution or probability function can be defined with the two parameters. One is the equivalent of the mean, which is me, and the other one is the variance. So if you understand where the centrality of the data is, and you understand how it's distributed, you actually know, in theory, knows the whole function. So if a random variable is normally distributed, the expected value is mu, and the variance is, I think this is delta square, or sigma. No, this is a sigma square. Okay? Hopefully you'll understand a little bit more when I show you some of the spreadsheets that I've got. Now, if something is normally distributed, here's the nice formula, which you don't need to know, but if somebody holds a gun against your head, this is the formula. So this function, which if we draw it, looks like this, and it's called bell shape, and you can see it's symmetrical, and it's got all kinds of nice mathematical things. That if you actually want to do it mathematically, this is the formula that you will have to use, where pi is 3.14 and e is 2.7182. If you put that into that formula, you'd be able to draw a graph like this. And we will do it just now. The shape of a normal distribution, it's bell-shaped, symmetrical. In this particular case, if mu equals 100, there you can see 100, you can fit it into this mathematical formula, and then suppose x is 110, which is that one there, and x is 90, you can do the calculation to calculate the area underneath this one. This is just to show it's symmetrical. So if mu, which is the average, is 100 and 110, and you do this calculation thingy, it comes up to the same answer as when it's 90. That's why we know it's a bit of a proof of it's symmetrical. You don't have to worry about it too much. How does the expected value affect the location of fx? As mu is getting bigger, you can see how these graphs are moving to the right. How does the standard deviation affect the location? That sigma, sigma. If it's 2, it's sort of like that, 3, 4, and so on. Let me show you a simulation which I've created for it. And hopefully it will explain some of the things for you. Come on. Sorry, I don't know why it vanished, but it did. I'll put the spreadsheet on Moodle as well. Okay, what I've done here is I've actually created this Excel spreadsheet which we calculate the values. Now, I've taken the numbers from minus 3.6 all the way up to 4.4 in this particular case. And here I've calculated this formula here, norm dist, is actually using that mathematical formula that we've seen. This is how you can do it in Excel. So you don't need to remember the mathematical formula, you can use it in Excel. And here you can see is the average or the expected value, which is that mean. And this is the standard deviation, or another word for it is that sigma symbol. And you can now see I've got a scale here, and I can move this around, and you can see how, if you look carefully, how this graph moves. If you look here at the bottom, the scale differs. Can you see? If I say the average is 2.7, can you see that this red line now fits exactly through that 2.7? If I move the scale that way, you can see that this red line now fits exactly through minus 0.2. Does it make sense?
Yep.
What happens if I change the standard deviation? At the moment it's 1. If I make it more, you'll see that again the scale change here. Can you see it's now flatter? So I can make it as flat as I want. And you can see here the bottom scale, it's very flat now. But the key is that this area underneath this curve must always add up to 1. So if I make it flatter, it's got to go wider. And if I make it less flat, this scale can be from -4 to there. If I make it 1, it's, there's 1. If I make it 1, and I make this one 0, 0, come on, 0. This is what's called standard normal distribution, and you'll see a lot about this, standard normal distribution. Now take a note, it's roughly from 3.6, minus 3.6 to 3.6, and this height is 0.4. But the key thing is this area underneath here always adds up to 1. Now I've got a different version of it. For instance, here, if I use a fixed scale, so even though I vary this, the scale of the graph stays the same. And it sort of gives you another, you can now see as I move the average or mean, the graph move to the right, or if I move it the other way, it moves to the left. So as you change the mean, this is what graphically happens. If on the other hand, I change the standard deviation, if I make it, it will make it flatter, flatter, more. So once I've got it flat, I can move this around. Does this give you guys any sort of insight, or you've got sort of?
Yeah.
This normal distribution, as I mentioned before, is very important. What is the area under this curve? What is the area underneath this curve? Anyone got an idea? What is the size of the area underneath this curve? Come on. With probability, it always adds up to 1. So the area underneath this curve always have to be 1. So regardless of how I move the scale around, this area will always be 1. That's what that mathematical formula gives us. Regardless of how you move it, it's always 1. Does that make sense? That if you calculate the area underneath here, it will be 1. It doesn't matter if you move it, it will still be 1. And that's how the normal distribution works. Now you can see here's the formula, normal distribution. And all you have to give it is the average and the standard deviation. And the rest is then calculated from there. Okay. Hopefully when we get to applications, it will make sense to you. Okay, you can see that my Excel spreadsheet has done this sort of in a more dynamic way. Now, how do we calculate normal distributions? 2 facts help us to calculate it. The one is the distribution is symmetrical. Did you see that? Regardless of how I change the graph, it's always symmetrical. And it's always got a specific shape. Any normal distribution can be transformed into a specific normal distribution called the standard normal distribution. The standard normal distribution is where the average or the mean or the mu is 0 and the sigma or the standard deviation is 1. By definition, yeah, okay. We can use the following function to convert any normal random to a standard normal by subtracting the average, the mu, and divide it by the standard deviation. And then, can you see here, regardless of what the value on the left-hand side is, you end up with mu equals 0 and the standard deviation of 1. Yeah, good advice, always draw a picture.
Did you say the mean equals 0?
If it's a standard if it's a standard normal distribution, a standard normal distribution,
Then the mean equals
0 and sigma equals 1. If it's not standard, it can be any value. What we do know is that this area under the curve always adds up to 1.
And you said sigma equals 1.
For a standard normal distribution, yes.
Yep. Thank you.
Okay. And here they just, okay. If we know the mean, all we have to know is the mean, and we need to know the standard deviation, then this whole distribution is defined. So we can use a table. I'm not really going to look into the table. You can look in your manual if you want to look at tables. I've not really used it, and I don't recommend you use it. Use the Excel spreadsheet formulas, and I'll show you how that works. Okay. So they go through how this distribution work. I'm going to, okay. For instance here, calculating the standard normal distribution, we want to calculate this. Let me go and do it for you in Excel. I'm going to, you can use the table, and if you feel strongly about it, do that. I'm going to do that same sum now using Excel, and that's how I recommend you use it. I'm just cutting this so I can take it to the Excel. Okay, give myself a new spreadsheet. And I just put whatever I've got there down here. So, as the recommendation was, always draw yourself a normal distribution or a curve just on a piece of paper, or I'm going to use Excel now to see what I'm doing. Insert. Okay, I'm going to insert a shape. The shape I'm going to insert is this one, I think. Okay, let's try again. This was not a good one. So I want to draw something that looks like that normal distribution. So I go insert, shape, this one. So I start there, there, there. Does that look like a normal distribution for you guys?
Yeah.
Say yes, otherwise I have to draw it again. It's sort of a normal distribution, isn't it? And it's also useful to just insert a straight line. Which is where the mean or the me is. Can you see that? Okay. Now, we know that this is 0, don't we? And this is sort of roughly 4. About 4. Okay. Let me just draw one more to make it. Okay. Does this make sense?
Yep.
Okay, so what is the probability that Z is less than minus 1.52? Okay, I'm just going to draw a line there. Minus 1.52 is roughly there, isn't it?
Mm.
Okay, so the bottom line is I'm interested in this area here. I want to calculate what is this area here. Do you agree? Because if this is minus 1.52, the area less than minus 1.52 is that one, isn't it?
Yep.
Okay, now I'm just going to use the Excel function which says equal norm distribution. Can you see it there? And all I have to supply is x, which is minus 1.52, minus 1.52. Okay. What is the mean?
0.
Right. And what's the standard deviation?
1.25.
No, it's just 1.
No, 1, yeah.
Yeah. And now I need to make a decision. Is it cumulative or not? And I normally guess true. And there you can see, so this area is 0.0642. And that's right. I know the area here, the area and everything less than 0 will be 0.5, isn't it? By definition. Because we say this is symmetrical and the 0 line is right in the middle. So this is 0.5. So I have a feeling that this is much smaller than 0.5. Does that make sense?
Yeah.
Okay, so now,
I have one question.
yeah.
when you're applying for the formula for the norm test, why you write for the in the last for the true one for the cumulative?
Okay, I'm glad you asked. I'm going to change this to false and let's see what the value is. Now that gives me a 0.125. Okay, let me try and there is another way of looking at this curve, and that is you can draw a cumulative distribution where you can read instead of reading in this particular case, we actually had, you can see mathematically, this is quite a difficult thing to actually do. You have to calculate this area. The mathematical way, it's called calculus or integration. You need to do integration to do this. So another way that they can do it, but I don't want to confuse you now, but I'll quickly do it, is when you draw a cumulative function. Now, if I convert this same graph into a cumulative normal distribution, it would look something like this. And in that case, the values here on the left-hand side, so if I want to read off minus 1.52, I go up here, and whatever I read off here is the actual, what is here depicted as an area is here depicted just as a line. Does this confuse you? Hope not. I think how I always remember it is I just try. Okay, for starters, if I put the actual value, if I put instead of this value, if I put in 0, what answer do I expect? If I put in normal distribution, x is a 0, I expect 0.5, isn't it?
Yep.
And that's what I get.
Okay.
And if I do it here, I'm going to get something else. 0.39. So I know that the false one is not correct.
Yeah.
Okay. So you can either learn it offhand or you do what I do and just play around. But because I've drawn it up, I know that the value I expect is much less than 0.5. So it's, for me personally, very or extremely important that you draw it before you calculate it. I'm saving you a lot of time not showing you how to do the table lookup and use Excel. This is 6 times faster than any other lookup technique that you can dream of. Let's look at another example. So let's see, here's the drawing that they've done, and there's -1. It's not as snazzy as my drawing, you have to admit. My drawing is much nicer and smoother, huh? Okay. So calculating standard normal probabilities, they, what do they try and say here? Okay, so here's another example where they say standard normal probability, how do we calculate this? Because they're using it. So in this particular case, let's go and do this particular one. Can you see in this particular case, we're asking a value that's bigger than the cutoff point. Where is this? Okay. Let's go back to my Excel spreadsheet. Adding one. Okay, if I draw, I'm just going to copy this graph because I'm too lazy to draw it again. Okay, so there's my normal distribution. We know again this value is here 0. We know this is roughly 4. And this is roughly -4. So what area we now want to look at 1.8? Do you agree that 1.8 is about there? Would you agree? 1.8. So we're looking for the area that sits here. So let me go and insert my squiggle. Freehand. Because it says greater than, we're interested in this area here. Can you see that?
Yeah.
But the Excel formula, though, only gives me, what's it, norm? It only gives me the value to the left. So in this particular case, I've got 1.8. And the mean is 0. And the standard deviation is 1 because it's a standard. Okay, sorry, it's 1.8. And we now know the answer here is always true. But you can see that this number isn't right. Can you see it? It's 0.9, which is big. We know it's quite a small area that we're actually looking for.
Yeah.
So because this is symmetrical, we know that the actual area I can also use to look at this area here. If this is minus 1.8, and that's 1.8, it's actually this area here will be the same as that area there. So it's all alternative. If I'm what is currently given to me is this area here. Let me insert shapes. This 0.964 is actually this area here. So I hope you can see, if I actually just want this area, it's 1 minus this area. Does that make sense?
Yes.
It becomes 1 minus. So to answer this question, it's 0.0353. What's the probability of Z greater than 1.8? It's the same as the probability of 1 minus Z less than 1.8. Okay, let's go and look at the slides if they come up with 0.35359, where they actually do it. And there you can see it's the same answer, 0.0359, 1 minus, because the formula only give me this area, but I'm actually only interested in that area. Okay. So calculating standard normal, applying the complement rule, we get this. Alternative using symmetry, which is what I showed you there. Okay. We can also calculate between two values. For instance, if I'm interested in what is the probability of it between minus 1.3 and 2.1, can you see that I just have to calculate the probability for this whole area minus the probability for this area. Does that make sense? Do you like me to show it to you in Excel?
Yes,
Please.
please.
Okay. Ah. Okay, I'm just taking this to my Excel spreadsheet. Give us another sheet. Okay, I'm not going to try and redraw this graph. You guys know what it is. So, for instance, so the probability of x less than 2.1 for a normal distribution is equal norm dist x is 2.1, comma, the mean is 0, the standard deviation is 1, and we know the answer here is true. Okay, and the probability of x less than 1 minus 1.3 is the next one I want to calculate. Okay. I use the same formula, equals norm dist x is minus 1.3 and the mean is 0, standard deviation is 1, and the answer there is true. So what is the area? It's actually this area now is given by the difference between the two. Do you understand how that makes sense? So it's this whole area here minus this little area here.
Yep.
That gives you the answer. Okay, so let's see if they also got 0.885. There you can see they've done exactly the same. They've used a table from the Z table, but you can look up in the book if you're really interested in using tables. I would consistently just use Excel. And you will have Excel available in all your exams and tests and so on. So forget, in my view, the tables. Okay. And here they talk again about the table. And table 3. Forget it. Okay. Suppose that at a country town petrol station, the daily demand for regular petrol is normally distributed with a mean of 1,000 liters and a standard deviation of 100 liters. The station manager has just opened the station for business and notes that there's exactly 1,100 liters of regular petrol in storage. The next delivery is scheduled later today at the close of business. The manager would like to know the probability that he will have enough regular petrol to satisfy today's demand. You do know that this is the real reason petrol prices or fuel prices change. Each store do this calculation. And if they know they're going to run out of fuel, they put up the price so less people buy. And if they have overstock, they put the price down. I suppose you've heard in the news that oil is selling currently at a negative price.
Yeah.
And it's because there's an oversupply. So people are doing these calculations a lot of times. So let me show you how we would calculate it. The demand for petrol is normally distributed with a mean of 1,000 and a standard deviation of 100. We want to find the probability of X less than 1,100. Graphically, we want to calculate the shaded area. Does that make sense?
Yep.
Yep.
Okay, let me take it to Excel and show you how I'll do it there. Okay, add another worksheet. Sorry. Okay, so I don't have to draw the picture again because you guys now know the picture. Now the formula slightly changed. Equal norm distribution. Now my X, what is my X?
1100.
11.
1100, you're right. What is my mean?
Is it 0?
1000.
Yeah, can you see here the mean is now changed, so it's now 1,000. So this is not a standard normal distribution. It's normally distributed, but not standard. Do you understand that?
Yep.
And the standard deviation is 100, and we know the rest of the answer is true. So that's as simple as this one is. 0.8413. Okay. Let's see if they got that. 0.8413. Okay, now what they've done is they first standardize it so that they can use the tables. You don't have to worry about this. Do you understand? Because we're using Excel. Once they standardize it, can you now see these values go from -4 to 4 and so on? It's a standard one now. And now you can go and look it up in tables and you come up 0.843. Who wants to use the tables? Hopefully nobody, because really in this day and age, it's like visiting somebody traveling on a horse when you actually got a car that sits in your garage. Okay. Okay. Really, if you want to use the tables, by all means, study it from the book. I don't recommend it. Learn how to use Excel effectively and efficiently. Okay. But in a drawing form, this is 0.8413. Okay, let's look at an application in finance. In 7.5, we developed an important application where we look at the returns of portfolio. However, we have not demonstrated why risk is measured by the variance and standard deviation. The following example corrects this deficiency. Consider an investment whose return is normally distributed. Can you see there it's normally distributed? With a mean of 10% and a standard deviation of 5%. Determine the probability of losing money. What does it mean, losing money? It means it's less than 0. Does that make sense?
Yeah.
Yep.
Find the probability of losing money when the standard deviation is equal to 10. So let's rewrite what's written here. There you can see the probability of X equals 0. So let me take this one. Let's do that one in Excel quickly. You see, it's so nice to do these things in Excel quickly. It's no problem doing a lot of examples. Okay, so the probability we want to look at is probability of X less than 0. That's when we lose money, isn't it?
Yep.
Okay, so all I have to do is fill in my form. Norm, distribution. X is, the average is 10. And whether you use percentages or not, it doesn't, no, sorry, 0. We want to know when the probability of it less than 0, where the average is 10, and the standard deviation is 5. And
True.
that is true. Yeah. Yeah, it's 20%. It's less than, it's 20%. The probability that I'm going to lose money on this is 20%. Will you do the investment?
No.
Yeah, on the other side, the upside is you can make money. At any rate, let's see the rest of the question. Find the probability of losing money when the standard deviation is equal to 10. So that's a good question. Okay. The normal way they wrote this, the assumptions in the shorthand, is normal distribution of, in this particular case, 10, which is the mean, and the standard deviation of 5. And the next question is normal distribution, but the standard deviation is 10.
Yeah.
This is just a shorthand, and we're still interested in the probability of that. I'm just going to copy the formula so I don't need to rewrite it. And all I have to do is change this to 10. Now, what do you guess? We know that curve is going to be much flatter, isn't it? So my guess is the probability is going to be bigger that I'm losing money. Let's see. Yep. 0.15 is bigger than 0.02. If we draw the little graph, let me not be lazy, let me, as I keep on telling to you guys to draw the thing, so let me draw it. Okay. So what does this mean? We know that in this particular case, we know that this is a mean of 10%. Okay. And we know that the standard deviation of 5, I'll tell you now, this is the value at the point here is roughly 3 times whatever the standard deviation is. So over here it will be, well, plus 10 is 25. And over here it will be times 3, 15, minus 5. And I'm interested in this area under 0. 10%. So I'm interested in a line that's roughly here. So 0 will be somewhere here. Do you see what I mean?
Yep.
So my interest is in this area that's over here. So insert shape, squiggles. I'm interested, yeah, except for that little bit that's outside there. So let's make it. I'm interested in this area here. Okay. Except for that little squiggle. Okay, and it's 0.02. Now, if I change the standard deviation to 10, this becomes 30, this becomes 40, and this becomes 10 times 3 is 30 minus 20. And that's why the probability here becomes a lot bigger because these tails are sort of bigger, if I can put it that way. Okay, hopefully it makes sense. Okay, example 3, let's see if they come up with the same example as us. Okay, they again first had to standardize it because they want to go and use tables. We don't need to do that. 0.0225. Can you see that this is the same answer that I got? Let's see. 0.022. Okay.
Mm.
So we write, and then if we increase the standard deviation to 10, this becomes 0.1587. 0.1587. Are you happy with that? Do you see how I've done that?
Yeah.
Okay, often we ask to find some value of Z for a given probability. So the question is, what is Z if I give you this probability? Can you see how that's the inverse of what we've done now? So if I say to you the probability is 0.2, what is the value of Z? Okay, so here they go through, how do we find this? What value of Z corresponds to an area under the curve? That is what ZA such that this is true. So we first have to, in this particular case, we want to do something that's bigger than that. Let me go straight into Excel and show you how I do it there. It's much simpler. Again, the last part has got to do with standardize it, which, have I mentioned it before? We don't have to do it because we're going to use Excel. So, okay, now the function that we want to use to answer this type of question is the norm inverse equals norm inverse. Can you see it there? Norm inverse. Okay. The probability we want to look at, the probability is that 0.975, no, is, yeah, it's 0.975 because we want the area to the left of this. To the right, so it's 1 minus 0.025 because they want 0.025. Okay, what is the mean? We know this is a standard normal distribution. It's typically depicted by Z. What is the mean?
0.
Yep. What is the standard deviation?
1.
Yeah. Let's see. 1.95. And can you see that's what they got to? 1.96, 1.9. If I round it, it's also 1.96.
Yep.
Okay. So I can ask you the question of what's the Z for, what is the Z value, or what value of Z corresponds to? And this is, again, a standard normal distribution. The nice thing of Excel is I don't need to stick to standard normal distribution. I can stick in any normal distribution. Okay. Can we take a 5-minute break, please?
Sure.
Yep.
I'm going to pause the recording. Right. Harriet, you still here? Anyone else here? There's Sharma. Okay, do you still see my screen?
Yep.
Okay.
Yep.
So the bottom line is a normal distribution is a very well-known distribution, and it's got all kinds of reasons why we want to use it often in our assumptions and so on. Remember, we on our way to do something where in the end we draw a sample and then draw conclusions and inference about a whole population. In order to do that, we need to understand a little bit about this normal distribution and so on. I hope it makes sense down the track. Okay. Here again, if z's a standard normal variable, determine the value of z less than the value of z. If you want to determine the value of z, you use the norm inverse function. Do you want me to do this in Excel quickly?
Yes, please.
Yes, please.
Okay. And I do suggest that you guys just spend quite a bit of time. You can see how quick it is. So there's quite a number of examples in the book. You know, just sort of work through it quickly. In the next quiz, I can tell you now, there's quite a few of these things in where I say the normal distribution of this shape, what is the probability? So in this particular case, we want to value of z for probability of z. Whenever you see z, you know it's a standard normal distribution. Okay?
Yep.
And that means the mean is 0 and the deviation is 1. So in this particular case, all I need to do is norm inf, the inverse. And the probability we're looking at is 0.6331. The mean, we know, is 0. The standard deviation is 1. And 0.34, and you can see that's what they got as well, using tables and all kinds of complex stuff. You can go and look it up, 0.34, or you can just use the Excel formula. And that's the one I recommend. As you guys know, we're actually translating this course from a statistical course to a business analytics course. So if you were studying statistics, we would have had a different emphasis on how you need to know the formulas. But because it's business analytics, I don't really think it's that important for you to know the formulas, except knowing it, how to do it in Excel. Does that make sense?
Yeah.
Yep. So I got one question as well. In this formula, so we know use for cumulative for the true or false when we find for the z value.
Yeah, in this, when you do the inverse, you try to get the z. So it being cumulative doesn't really make sense.
Okay.
So just accept that for this one, you don't use the true or false. But as you've seen, when I keyed it in Excel, if you start and you say equals norm,
Mm-hmm.
and it gives you the option for the inverse, you know you need to use the inverse because you're going to calculate the z.
Yep.
It tells you the probability. It tells you need to supply the mean. You must do the standard deviation. It doesn't ask for a true false answer.
Yeah.
Where
Thank you.
if in the same case, I start keying in norm and I want the normal distribution because I want to calculate the probability, it then prompts you to what's the x, what's the mean, what's the standard deviation, and then up to the cumulative, that's the true false one.
Yep.
So if you eventually it becomes second nature. If the formula doesn't ask for something, you don't supply it. It's simple. And you can see me, I'm not always clear whether it's cumulative or not. but I can just test it with my own logic.
Yep.
Okay. It's interesting to note, but you don't need to know it, but a normal approximation for you remember the binomial distribution, which we did last semester, where it's two values, and I've shown you the example of the red bead experiments. If the sample size is large and the probability of success P is close to 0.5, you can actually use the normal distribution and these formulas to calculate it. Let me think about it. I won't, let's see if there's a particular example and I can show it to you. Okay, let's look at this one and I'll show you in Excel. Again, I'm not really interested that you understand the maths between why it's like this or not, as long as you can do it in Excel. And again, in Excel, you can do the binomial distribution. There's formulas for it. So in that sense, you don't have to worry too much about it. Is that okay? So
yep.
Let's just check this one. If, for example, I do this example in two different ways, one using the normal distribution approximation and one using the binomial distribution, let's see what it comes up with. Okay, so binomial distribution with a normal approach, where did these values come from? I thought this was a little sum or a little example. Okay. Let me just think about it. In 20 and P is 0.5. Okay. Just think what I want to do here. No, okay, I haven't thought it through. It's not extremely important. If I think it's important, I'll deal with it next week. Take note, you can use the normal distribution to approximate the binomial distribution. Let's see, please. Okay, exponential distribution is another one. I just want to show you the exponential distribution is something that looks like this. So is this symmetrical? No, it's not symmetrical. What we do know is that under this area, it adds up to 1, because that's the rule of these distributions. Okay, and it uses symbol like lambda. There might be some in the quiz, but I won't ask you about the exponential distribution. It is slightly important because it's often used to calculate the lifetime of something. So the lifetime of an alkaline battery. And if you think about it, you know, the battery, the charge in a battery decline, but then it sort of slowly decline less and less. So it gives you that curve that we've looked at. It gives you this type of curve. Yeah, we won't really look at it any further beyond this. Okay, well, took me a bit of longer to cover tonight's subject matter, but there we've done it. I thought of just having a look at, hopefully I've got it, let me just have a look here. I'm just going to look at some coronavirus graphs. Let me just see if I can bring it up quickly. Okay. Here's my thinking about the assignment. And I obviously want your feedback and what your thinking is. Instead of putting a heavy emphasis of you being capable of analyzing and drawing the data, the graphs yourself, I will actually, as part of the assignment, do at least half of them and ask you to draw conclusions from it. So less emphasis on you drawing the graphs and more emphasis on, there will be some, so let me not kid you, there will be some, but primarily I'll give you an example and say what conclusion can you draw. Now here, for instance,
what do you mean by that, sorry? Just in conclusion, just.
So you remember we said the assignment will be a report.
Yep.
So I'll draw at least half. I'll give you, this is the analysis that I've done. I'll give you an example now.
Yep.
For instance, yep. I can ask you, what is the total confirmed deaths per million? For instance, I can say to you, show me the graph of the cumulative deaths per day for Australia.
Yep.
So I'll show you how proper dates.
Yep.
Did you guys come related to coronavirus that you found interesting or wondered about? Or I do encourage you to, have quite an awareness because it's actually quite fascinating. Just something simple as how do they measure whether somebody has got the virus or not? Found the one I actually was interested in. Okay, now we're cooking with gas. Okay, here's the raw data. So I've got country, and I've got the number of cases. This was on the 8th of April or somewhere there, so it's quite old now. I'll update one. And one of a simple question is which countries, and if you look at these variables on top here, can you see that the only one where if you want to compare a country with another country, you actually should only look at these calculations here: total cases per 1 million, deaths per 1 million, total tests, and tests per 1 million. These other ones, it's relative. If Afghanistan has got 422 and Australia has got 5,900, maybe Afghanistan, the rate is more than Australia. Do you understand that? So you need to look at these variables, that's per 1 million. Do you agree with that? I mean, all the other stuff is interesting, but if you want to compare two or more countries with each other, you need to look at these variables here. So let's look at what I've done in, for starters, I said, let's look at these three variables and calculate the min and the max and the 50th percentile and so on. So we now know the expectation of any country, 76 is the median of cases. And deaths is about 2 per million. And the number of tests being done is about 2,000 per million. Does that make sense? So I'll potentially give you this table and say, okay, interpret it for me. tell me what you now know about all the, across the world, what is the medians and so on. And you need to be able to discuss it. Let's look at sheet 3. Here's, here I calculated the mean and the standard deviation and the median and so on. Again, the total cases per 1 million deaths and the test per 1 million. Sheet 4, what did I do here? Okay, here I've done a standard histogram. Again, discuss it. You can say to me 70% of it is between 0 and 100 deaths per 1 million. So it's about 100, 0 and 100 deaths per 100 million. Sheet 5, what did I do here? Here I compared 3 countries, Australia, India, South Africa. And again, the average, you can see that the average total cases, there's a lot more cases in Australia compared to India and South Africa. And the number of deaths is much higher than India or South Africa. But we've also done a lot more tests. Can you see we've done 12,000 tests for every 1 million people. Where in India and South Africa, they've hardly done any tests. So that explains why there's so few total cases. Do you understand that? They didn't test a lot of people. They tested hardly anybody. And even these deaths, if you didn't test it, you don't know if somebody is coronavirus when they die, you wouldn't know. So my view is that this is a total underestimation of what's happening. Say, for instance, we bring in, okay, if I go back to this data and I do the same thing, insert pivot table, and I want to compare other countries, filter, okay, country, let's just look at deaths per 1 million. No, sorry, I need to put it there, and I want to put the country there for argument's sake. And I can now filter on which countries do you want to look at? Australia. Should we look at India? And the US, and the UK.
New Zealand?
Yeah, that's a good one. We pass it, New Zealand. New Zealand. One that's interesting is Sweden. You guys probably heard that Sweden has done nothing.
Yeah.
Okay, so now we know, let's just, okay, so we don't want the sum, we want the average. Because the sum doesn't really make sense, does it? We want the average. Okay. Although, because there's only one value in our data set, that's what we get. So let's see, Sweden, can you see how high their deaths is? It's all very well to say, oh, we're not going to do anything, but there's 25 times more people die there per million. Can you see that?
Yep.
Yeah.
They've got 3 times the number of cases that we've got.
Oh, well.
So it's all very well to say, look, we're going to ignore it, but the actual result is pretty high. On the other hand, my suspicion is that, okay, New Zealand, they on par with the number of cases, but very few deaths. So they obviously treat people in hospitals very quickly and efficiently. Let's just bring back in the United States. From what I understand, the Ukraine is also ignoring the whole thing. Yeah, United States, they've got a lot of deaths, isn't it? They tested a lot more than us, but look how high their death rate is. They, in fact, not far behind Sweden, and Sweden do nothing. Okay, interesting. But I will, okay, let me have one more. It must be somewhere else where I've actually, let me just, I've done a lot more work on a more up-to-date data set, but I can't find it now. Let me just have one go at searching for it. Okay, let me in the meantime go back to the course. You guys can still see my screen, can't you?
Yeah.
And now something happened. Okay, let me just look here at our schedule. Come on. Yeah, I'm still grading the quizzes, by the way. I'll get that through to you hopefully soon. Okay, so where we are at the moment is we've done this continuous probability, and then we're going to look at statistical inference and how do you draw conclusions from samples, and then we're going to look into estimations, how to describe a single population. And then looking at hypothesis testing, is one better than another? So my aim is to release the assignment next week, or as soon as I can, hopefully Friday. So you can start working on your assignment. I'm not 100% sure it will be on COVID-19, but maybe. But I will do at least half of the analysis, so, and then you can talk and discuss about what it is, and then there will be some where you have to do the histogram or the line chart or the descriptive statistics or something like that. Make sense?
Yep.
Yeah.
Okay, so we're in the last, what, how many weeks? 1, 2, 3, 4, 5 weeks really, because this is just review of everything. So we just got literally 5 more lessons. Hang in there, do lots of examples, and you should be okay. I think I'm gonna call it a night now, one, because I'm tired.
Yeah.
Okay, any questions? Anyone that would like to discuss, bring up something they come across or something?
So quiz 3 is held in a week 9.
Yeah, is that, let me just open it up again. Yeah, quiz 3 is on the 11th of May.
Okay.
So it's 2 weeks from now.
Yep.
And it will cover everything up to chapter 11. I haven't set it yet, so I don't know what all will be in it. But I'm trying to refocus it away from calculations more to interpretation. So here's the result. What do you see, or how do you understand this? That makes sense?
Yep.
Yeah.
Okay, anything else?
No.
No, good.
Have a good night and have a
Thank
good
you.
rest of the week. Watch the discussion forums. I hope to put a couple of things out there. And by all means, pose whatever questions you want, pose it there.
Okay.
Thank you.